Hello everyone, and welcome back to a new episode of SHENZHEN I. We are here in the studio with Rose again. Hello.
Hello.
She came by to join us for at least one more new puzzle. Who can say? Some of them have been long, some have been short. And we are moving on next to building what? A pollution sensing smart window. Sounds useful in SHENZHEN. I'm working on a smart window that reacts to particulate matter in the air, i.e. pollution. I need a controller that allows us to close the window when the level is too high and opens it again when the level is lower. This sounds a lot like, I'm sure it will be different, but it sounds a lot like one we did really, really early. Where is that? The audio alarm, right? Not audio alarm, the infrared... Was it the infrared sensor? Yeah, right? We implemented like an alarm clock, not alarm clock, a house alarm where like the user set a time and there was a thing, and if the value of this thing was high when we were within the time, then we sent like a thing. And it sounds a lot like, I don't know.
What a helpful description.
I mean, they watched
there
that.
was a thing and a thing and a thing.
Yeah, okay. Wow, we have kind of a small footprint to work with this time.
Yes, we do.
Sensor is a simple input connected to an air pollution sensor. Window is a simple output connected to a motor that opens and closes a sliding window. The window should be closed, signal low, when the average sensor reading for the 8 most recent time units is greater than or equal to 50.
That sounds like RAM.
Yeah.
Is the RAM rolling or is it?
Yeah, it's what do you mean when you say rolling?
I mean, well, what I meant was how does it tell you? I don't think that I meant a helpful thing.
Okay. So the RAM, every time it has 2 independent read-write pointers.
Okay.
And every time you read or write from one, it increments the pointer.
Okay. Presumably you can set the pointer?
You can set it, yes.
Okay.
So...
Can we ask it what the pointer is pointing at?
Yep.
So it seems like what you want to do is write the sensor and then subtract 8.
Subtract 8?
So set into the RAM the value of whatever the sensor is.
Yeah.
And then from that pointer, subtract 8 or 7.
Sure, you could, right.
And then cycle through. So you leave one pointer in the same place all the time. Is my suggestion.
Leave one pointer in the same place?
Sorry, you leave one pointer as exclusively your writing.
Yes. Yeah, I mean, I think that sounds about right.
And you move your read pointer.
Yes. It seems like there's got to be some smarter way to do rolling averages, though, right? Like...
Sure, I mean, you can subtract the last one and add... So you can multiply by 8. I assume you can do that.
We don't want to multiply by 8, we want to divide by 8, right?
Well, we're going to have divided by 8.
We actually don't have a division instruction, like FYI.
Oh! Well, that's exciting!
Yeah.
We don't have any kind of division instruction?
I mean, we can go look at the language reference.
And we don't care, right? We don't care, because we just multiply by 8 on the other side of the equation. Right, if the average is greater than or equal to 50, then we just need to make sure that the sum is greater than or equal to 400.
Sure. Yes, that's much better.
It's good that we don't have a division instruction. We're about to do something stupid and unnecessary. Okay. So sure, and then you can just add the latest one and subtract the one that's fallen off.
Right, but yes, you can do that, but there's then like some special casing for like, how do you get the first 8 things? Like...
Sure.
And actually, what do you do if... Let's look at some of the inputs, like...
Sure.
What if the first reading is 50, right? Or is it 100?
Right, well what does it do
I
then?
think we don't have any of those, I don't think. We might have some in, like, the second test, but you're not allowed to look at the second test, which bothers the heck out of me.
A little bit.
But it does say for the average for the last 8, so, like, that can't be true if you haven't had 8, right? Yeah. So one thing we could do, maybe...
Just initialize it to zeros, like...
Well, so what we could do is, I was thinking, like,
I think if you just initialize it to zeros, it'll be fine.
Well, initialize what, the RAM?
Yeah.
It's already zeros, but
then it's fine.
but I'm trying to avoid having to do a sum of 8 things every cycle by keeping track of what the sum was last time.
Right, so your
adding
sum,
a number, subtracting a number.
Your sum initializes to 0.
Right.
The RAM initializes to 0.
Yes.
You start one pointer 8 behind the other. You're done. You just add and subtract. You don't have to sum all 8. You're very confused, and I'm not sure why. So we have 4 moving parts.
Okay.
We have the RAM, which contains all of our sensor readings. We have our rolling average, which we initialize to 0. We have our write pointer.
Yeah, right.
We write and we add. And we have our read pointer, where we subtract, which is 8 behind the write.
Since the RAM is all zeros, it's going to be okay to subtract the 0 that was 8 behind the current write head.
Exactly.
Okay. So we don't need a special case for the first 8 inputs.
Yes.
It's going to be a little bit tricky, I think, to actually arrange to read, to move the right head pointers around in the way that we want. Seems a little bit tricky.
Can we not just initialize, do our very first piece of initialization by putting the right head pointer 8 ahead and then just never letting it go back to
Of course. But if we're writing... okay, so I was thinking that we would need...
Or a read head pointer back to -8, but
Sure.
either of those.
Yeah, I was thinking we might need to, like... It's kind of hard to write a value and then immediately read it back.
Okay.
Right? Because you've written and you've moved the pointer. And then you have to like ask what the pointer value is and then do some math on it. Like, it's hard to do math cheaply, right?
Right, but what we put it in the we'll have it, so we just put it in. Well, why would we use a RAM at all if we're using a rolling average? Oh, because we need to know what's 8 back, right?
Right.
But that's okay. We don't care. We don't
So
need to be able to read it from the.
Right. So
the
as
thing.
long as I was imagining there were 2 chips, one of them doing writing, one doing reading. In which case it's hard to orchestrate.
Right. No, you just need 1 chip.
I think we could very easily run out of code space on 1 chip, but if
Let's
we
try
can
it.
use 1 chip to do most of the work and another chip to do something dumb, maybe.
Yeah.
Okay, so here's our RAM. Great. And we're certainly going to need a large chip.
I agree.
MC6000, I believe, is the title. We'll wire up its simple input to here.
Okay.
And so if we really are going to be able to do it with a single thing, then we're using up all 4 of its X buses to connect to its 4 heads.
Okay.
Which is fine. It just means we won't be able to communicate with another chip if we're gonna like do it this way. Which is okay.
Yeah. Well, we'll start with this.
Exactly how to wire it is another little bit of a puzzle, but I think we could do it like.
That's a simple output.
Yes, it's going over here.
Okay. Just making sure.
Alright, well, let's wire up something like this first, since it seems a bit tricky.
Okay. That goes to the other one that's on the bottom. That will make you the happiest.
Yeah, we're not going to have enough wiring space, right, to get all 3 wires we need. There's no space that's 3 wires wide, right?
Interesting.
We need to get them all over there. So,
okay.
So I think we need more than 1 chip.
Or we could use just 1 pointer on the RAM.
That's so hard, because you're going to have to read the pointer, decrement 8, read, add 7, like,
Okay.
and then write. So that's like, for every operation, a lot, I guess. I don't know. Maybe you can fit it, but it seems like that's spending an awful lot on I/O.
Okay.
But I don't know. Maybe it's not.
Yeah, it's not that, because we don't have that many operations to do, right? We've got one operation, essentially.
Mm-hmm. Well, okay. Let's try being like what I would describe as somewhat optimistic.
Yeah.
And let's say we can do it like this.
I agree. And then we don't have to initialize because we're not maintaining pointer state, which is nice too.
Sure. Okay. So what we're going to do each cycle is let's see. I guess we just start by moving P0 into the onto this thing.
Okay.
Yeah, and then we'll add P0 as well to our accumulator.
Yes.
That's the one problem with having a single chip is that we need to do two kinds of math now.
Right, but we can move it to the DAT to save it.
Yes.
And then come back.
But you can only do math in ACK, right?
I see. Yes. I see the issue. All right. Well, let's use two chips then.
Okay. The wiring for that is also, I think, relatively simple. Let's scooch this over a bit. So, actually, this is fine. We can wire this up to the other thing. So let's have this guy exist. His,
let's make this a small one and just make its job to be making sure the pointers point to the right place.
How? What?
So if there were a small chip here.
Yeah.
And it just... Oh, well, that doesn't make any sense. Sorry, don't mind me.
The problem is that, like...
Explain to me how the RAM inputs work. Let's start with that.
Okay, let's go read the specs. I know what they are, but it'll be handy to have them on screen. And so RAM, can I search for RAM and find it? No. Program. Alright, what the hell is the name of this part? It's a 100P-14.
200P-14.
Really?
Yep.
Disagree.
You seem to be right.
I mean, so this is random access, memory pointers, read and write. Yeah, this is the RAM.
Okay. Nope, you're totally right.
Okay, so there's two address pointers and two data pointers. They're connected to each other. So they're independent. When you read from data register 1, you get what's at address register 1.
Okay.
They initialize to 0, as do the pointers. You can read and write the memory pointer over address pins. You can read and write the values over the data pins. And anytime you read or write, the corresponding memory pointer goes up by 1.
So hang on, we don't have to change the address pins at all.
We do if we want to.
Right, so let's just put in a tiny chip that moves our secondary pointer and then sleeps forever.
We don't have the wiring, right? It was not possible to connect to all of those.
We don't have to connect to all of these. We only need to connect to the data pointers from this chip on the left. Because we want the incrementing to happen always.
All right. Okay. That's interesting. I can see how that might work. So let's do something like data, and
you might be happier if you move everything down one.
I think?
Yeah.
All right. I'm not so sure how this has helped, but okay.
Well, you know, maybe I'm wrong.
We're gonna need to cross some more wires here, aren't we?
Yeah, unfortunately.
Let's bridge this up.
I was gonna bridge the other one back down, but you know, what do I know?
It's kind of hard because, anyway. The problem is not this wire, it's the one that's coming in from here that has to get to A0 somehow.
You need to move the RAM left one so that you can hook up D1.
Do I need to? Oh god, I do.
That's fine, there's room.
Wait, What?
Remove the RAM left one
Why?
so that you can hook up D1. Because otherwise it was going to wind up at X0.
Was it?
Wasn't it?
No.
Oh, I misunderstood
Right?
the wiring.
We
Okay.
could, for
Oh, we
example,
can
go
do
like that. Well, equivalently, we could have gone like this, and that also works,
Oh,
right?
I just didn't think that worked.
But the trick is getting this one to bridge over that, right?
Well, we don't need to. We only ever need that to do that one thing.
Because we can leave one of them initialized to 0.
Yep.
Okay. Okay, so where's this one going? We're connected to D0.
So we want to connect to D1.
Yeah. Okay. And this guy is connected to the only place he ever needs to go.
And it needs to set it to 8 and then sleep forever.
So we could do that here if we could wire it up.
Yes, I agree, but this will be easier to set it to 0 and then sleep. This is also easier because now you can just make it sleep forever and you're not losing lines of code. You don't have to figure out how to not reinitialize.
We want to set it to 8, you think? That sounds... 7, I think. Yeah. Move a 7 to X1.
I don't know, I need a piece of paper and to write it out to figure out for sure where we want it, but... Perfect.
So there's that. Now, this guy's job is to, let's see, first we're going to move...
do we want to sleep one first?
No, why? What?
I guess I'm just concerned about waiting until after it's moved, but I guess we don't care.
Yeah, that's going to happen real fast.
Okay.
We just won't read from that one first.
Okay. So we want to add P0 to our accumulator.
Well, first I'm just going to put it into X2.
That's fine.
And then we will add P0.
And then we want to subtract.
Right, subtract what's on X3.
Yes.
Sub X3.
And we can do that, or I guess so, okay.
Yeah.
Okay.
Should be okay. And then we just say,
if it's over...
Yeah, so
100.
if... No, we're not, the specs aren't over there. If it's greater than or equal to 400. So,
Is it TGE?
No, it's GTE. I'm just, J is test greater than, so TGT.
But is there not a TGE? I guess
test greater equal? No.
Okay.
But we don't need one, right? So you just invert test less.
Right.
I'm just trying to think about if there's a problem with the way that we're simplifying, because let's say that the input is 100 for 4 cycles in a row.
Uh-huh.
The average will have been, like, we will say, the total is greater than 400.
Uh-huh.
That means the average over the last 8 must have been greater than 50.
It is.
But it hasn't been because we haven't gotten 8 inputs.
Right, which was the concern we started with, but I think it's okay.
Well,
look at the test.
Well, the tests are not very thorough, right?
Sure.
I mean, they start out low, so, like, maybe that's... What a nice coincidence that the first 4 are 0. Like, is it going to be that way all the time? Who knows?
Well, let's try it.
Yeah.
This is not the most rigorously tested
So what we're going to do
ever,
is test greater than... Or, damn it.
You wanted a less than you decided. 400.
Well, you can also test greater than 49. I mean... Or,
399, sure.
Yes, 399. Right. So, ACK 399. If so, move, I assume, 100 to window. Window should be... no. Signal low. So move 0 to P1.
Oh, we'll
Otherwise,
need to start by signaling the window high, won't we? Then.
Sure.
Can we just do that? No, I guess this is probably better.
P1. Okay. And then, like, sleep 1. So, in theory, this is the whole thing?
And does it not run that?
That's what the at is.
Okay, it only runs that, doesn't it?
It says run that once,
okay.
Yeah.
Perfect. I think that's it.
I am very dubious about this.
Let's find out.
Yeah. So we opened the window, great. This guy has initialized the pointer to be here.
Good.
We'll write here. Wait.
Right.
Wait. We don't want it to be 8. We want it to be like 14 minus 8, right? We want it to be negative 8, not 8.
Why?
We want to read what it was 8 ago, not 8 in the future.
Well, it depends on which way you've got it around.
The one that this guy is setting is the one we're using as our right. Oh, right? I actually
as our solid.
As
well,
our
then
as
you
our
need to write
label.
it somewhere else. Yes.
I think we want to send this to minus 8, which is like 6. I think.
Well, 14 minus 8 is 6.
Yes, I know. I mean, that's pretty clear. I guess we'll see.
Yeah,
I
I was doing it the other way around in the things, but this will work.
So we added P0 and we subbed
X3.
X3. I guess this moved up and yeah, right, it started here.
Yep.
Okay. Step. So that means 0 through. Oh, I don't know. I'm not so
I'm
sure
gonna
about
count
this.
these. 1, 2, 3, 4, 5, 6.
There are
No,
four-
it's definitely 6. 6 is the wrong number.
Alright. So let's see. We're going to write a value here.
Uh-huh.
Well, actually, let's step into the future and write a value here.
Okay.
Right? The one we need to read is 1 back, 2 back, 3 back, 4, 5, 6, 7. We want to read 8 back, right?
Yes.
Okay. So this one is at index 2.
Yes.
I already forgot which one we started reading.
Well, let's count
2,
forward
3, 4, 5, 6, 7, 8. This one is at index 10. So we want to put an 8 there, I guess.
Yes.
No, wait. When we read from 10,
Uh-huh.
when we write to 10,
Uh-huh.
we want to read from 2,
Yes.
which means that at all times, the write pointer should be 8 ahead of the read pointer,
Yes.
which means that if we're initializing the read pointer, it should be to minus 8, which is 6.
But it wasn't in the right spot.
I'm not so sure.
Okay, well, let's start it up.
I don't know if I believe in eyeballing that much. So one thing we could do is step forward 1, 2, 3, 4, 5, 6, 7. This will be the 8th input we receive.
Okay, let's do that.
Now we have indeed written 7 things. We're about to read the 8th. Sorry, we're about to write the 8th.
Yes.
And then after we've done that, we'll read this, which is still 0.
Okay.
And then once there are 8 things, we'll start reading the first one.
Okay.
So I
you're
think
in the right
6 is
spot. You're in
correct.
the right spot. Okay.
Let's make sure our accumulator, 132, is the sum of all these. We didn't mess that up somehow. Yes, it is. Okay, sounds good.
Yep.
So let's just go ahead and read that one in. Yes, now we've got the right thing, and we're all set to start reading the oldest value.
Perfect.
So, and in fact, since the oldest values are all zeros, like nothing interesting is going to happen to them. Our values 332, it's about to go up by 100.
Yep.
As polluted as possible.
Yep.
So we'll just go ahead and do that, I guess. Here we go. There's the 100. Subtracting the old value. Is it greater than 399? Yes. Shut the window.
Woohoo! We
Great.
did it!
So now's the first time we're reading an old value.
Yep.
Let's make sure that happens okay. Write a 0. Subtract the old 33, and indeed the measure has gone down because our current value is 0 and the old value is more than 0.
Yep.
So I think this looks okay.
Looks right.
Yeah. Now this chip bothers me a little, right?
Sure. I mean, we can also make the other one
Mm-hmm.
the other one a small chip too. I don't know if you noticed.
No, we're using too many of its wires.
Are
Oh,
we
no, we're
probably
not.
using 4 of them?
No, you're right. Yes, and it does all fit here. So the thing is, though, if we want to remove this one,
Sure.
that's better than downgrading this one,
Okay.
right? This is 3 and this is 5, so we'd rather have 2 3. We'd rather have a 5 than 2 3s.
Sure. So there should be enough room. Because you don't need to hook anything up to A0 at all.
But like,
Or anything up to A1. Either way. So.
but how do we get enough vertical space to do this?
So what you would do is you would move this chip over, move this chip.
This one here.
Yeah, over to the right of you.
Sure.
And you would hook up the 2 wires that are there directly.
Fine.
And then you just need one to come out on the left and bridge over and come down. And your P1 can just go straight across.
Let's see. Well, you say hook these 2 up directly.
Just like that.
I see. We would use a 0 and not a 1.
Sure.
It means we'd need to change which is the read head and which is the write head, but that's okay.
Or we can just move a different number.
Put 8 into the right head instead.
Yep.
Okay. All right. So we should be able to do that.
Yeah. So that's a trivial optimization, right?
If we do, we'll still need a large chip here.
Yes.
And I don't see a way around that, except... So... We're going to need at least 3 X-bus wires, right?
Yeah.
And 2 simple I/O pins, which requires a large chip.
Yeah.
But if we grabbed this little guy with 4 X-bus wires and connected a muxer up here, we could then send either a 0 or a 1 over X-bus instead of over the simple I/O.
Right.
And we have a total of 9 instructions on here.
But we just counted out 5 wires. Not 4. Right, we need an input and 4 outputs.
You're right. We can't...
Let's do the first optimization and then come back.
All right. I think we actually could do it. Because like.
Well, let's do the first optimization and then come back to it.
Fine.
So get all these junky chips off.
Yeah.
And you're gonna move stuff to the right.
Yeah. Let's get these off. Let's just throw everything. Because like. It seems like we can do this like super cheaply, and it's rare that I get to a good solution, and it feels like this must be one.
Yeah, this is a great solution.
Alright, so the first thing, as you say, well, where is you, Max? I don't trust, look at this is the last thing this year is a different puzzle. Alright.
That was the sandwich maker.
And let's also, just while we're here, move a...
We decided
8 onto, for now, I guess it's x2, but not x2, no. It's going to be some other thing.
We'll fix it.
Okay, so throw this away. Oh, no, we still wanted the big chip.
Yeah, we still wanted the big chip. I was like, why are you doing this?
Because I was getting all excited about this.
No,
this
we're
little
doing
guy.
this initialization, this optimization first, one at a time.
No, that's the wrong one.
It very much is. Alright, I mean, we're gonna have to move our pins around, but that's okay.
Yeah.
Alright, so you're moving this to the right. Let's do that.
Yeah, okay. Like so?
Yep. And now we're gonna connect straight on
Actually,
the
it would, even more would be good, probably.
Probably.
Well, yeah, right. So connect these up.
And then you can connect P1 straight as well.
Yes, straight-ish.
Totally straight. Look at that. And now grab one of the X's on the other side and pop it over.
Okay, so now here...
Alright, so first...
We are at moving 8 onto... Oh no, we have access to both of these, so it doesn't
you
matter.
put it on the address instead of the data, by the way.
Put what on?
X0.
Oh, you're... right, okay, yes. I did that on purpose, but I was wrong.
Okay.
Move 8 onto
X3.
X3.
It did not take your time.
Hello, space. There we go. X3. Okay, so are these wires all correct still? We're moving 100.
No, it's definitely, we're gonna have to move some stuff.
Move P0 onto X2, that's the right place.
Okay.
Add P0, that's right. Sub X3 is wrong. We want X0 now, yes.
And the rest of that looks right.
x0, but we're never using. Where are we using x0? Sub x0. Okay. Sub x0. I don't know.
Literally the line you just wrote.
Yeah. For some reason, I don't know. This made me think of like Sub-Zero Mortal Kombat. I don't know why. All right. So that all still seems to work.
And is a much cheaper solution.
Yes, but I think it could be $1 cheaper.
I think you might be right. But I thought we'd start with this.
Sure.
Somebody got a way cheaper.
Nobody has made it $1 cheaper. They have made it $2 cheaper.
Well, what's $2?
Throwing away, like...
The RAM?
Well, no, the RAM is 3, isn't it?
Well, what can you use instead of the RAM, then?
So we could make it $1 cheaper, I think, by using this guy and an IO expander.
Right.
I don't think we can do much with this.
Yeah?
Like, you would have to solve the whole problem with that.
Uh-huh.
I don't think you can do that.
Maybe you can, I don't know. Just write a truth table somehow. It doesn't seem likely.
No. Yeah, because you need to implement an adder in here somehow.
Right.
And also initialization. This is not a controller, I don't think.
Right, I agree. I don't think that's a solution.
So, we've got all this.
Uh-huh.
And I think we could, as I said, use a muxer and a smaller chip. So, let's try it.
Okay. Now you want to save that code.
Yeah.
Did you put an Emacs? Because it's slightly different code.
I didn't, but it's in my buffer, in my base buffer. Whatever. There it is.
Just in case.
Yeah. So, alright, let's wire this all up. Like, it's gonna be a little crazy.
Yeah, I don't know that you've got the space for it, but go for it.
Yeah, I guess we don't have the vertical space. That's kind of sad, isn't it? Like, maybe if we did something like this? Actually, this could be over quite far.
Yeah?
Since we just need to be able to get in, like, well, not that far, huh?
Yep, but you can put it there.
Need to do that. This goes up here.
Okay. So how are we getting an extra input? Because we had 5 wires on our big chip.
This
I see.
is going like that.
I see.
Okay. And then this chip needs to somehow become like the master controller of the whole universe.
Okay.
Which I think we can do, right? This goes here.
Okay.
And this goes here, and we're in, right?
Okay. Those are the things that need to be hooked up.
Yeah.
All right, now do it.
Now, this is where I might run afoul of the rules of this thing. Like, were you here when I didn't understand how this thing...
No, I don't think so.
See, it turns out you can't use this as a 3-bit storage mechanism for some reason.
Okay.
Because it has like a read mode and a write mode, and when you read from it, it goes into read mode, and when you write to it, it goes into write mode, and like... So you can't write a thing onto this pin and then ask it what is the value of this pin.
Okay.
But fortunately, we don't want to do that.
Right.
We want to write to this pin and read from this pin, and we should be all right, I think.
Okay.
So what we're gonna do is move 0. How did question marks get here? I didn't read. What? Get out of here. Okay, so move 8 onto
the address, which is extra, so you're still right.
But no, we want it to be onto x3. Okay, good. And then 100 onto P1 is not correct. We want to write
100 to X1.
It does want to be 100 as it happens, yes.
I checked.
And then we want to move... interesting.
Now we've got a sleep for it.
Oh, of course. We can't do this because this only gives us a binary value.
Yeah.
Okay,
I did
right.
wonder.
Well, you didn't say.
Well, you seemed very sure that you could make a better optimization.
Okay, so we needed... All right, so our solution was as good as we could do with the parts we understand how to use.
Okay.
So I'm not going to put it all back. I hope you guys who were watching this enjoyed...
Just take a screenshot.
...the last time that puzzle will ever be solved. And let's go read our accolades. Good. By the way, maybe you noticed that this is a sliding window algorithm for a sliding window. Do you think that's funny? I do. Thank you, Mr. Zhengji? Zhengji?
Bob.
No, Zheng. I don't know. I don't know the difference between a ZH and a J, honestly.
I mean, I'm not the person to ask.
Yeah. Anyway, so we're done with this puzzle. Hope you guys enjoyed. Thanks for watching, and I will see you next time.